All right, we have looked at finding the sum of a geometric series like this one below. Notice the first term is 1. Notice the common ratio, r, is 1/2. And notice there's 1, 2, 3, 4, 5, 6 terms, so n is equal to 6. I can find the sum of the first 6 terms by substituting it into our finite geometric series formula. A sub 1 goes right here. It's 1 minus r to the n all over 1 minus r. Notice that sum, after I clean things up, becomes 63 over 32. By the way, I know 64 over 32 is equal to 2. This is just a little less, so this is close to 2. I just want you to keep that in mind as we look at something, look at this again later. But what if this series above doesn't stop after 6 terms? What if it continues on forever? So it looks something like this: 1 plus 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus 1 over 32 plus 1 over 64 plus forever. So the question is, what is the sum of an infinite geometric series? We're going to look at this one below. But after we look at some examples first, this one's classic. It's kind of fun to look at, but we will end with this. So, some introductory work. An infinite geometric series will converge, which means it's going to have some infinite summation that will become a number, not infinity, if the absolute value of r is that common ratio, is less than 1. So if r is between -1 and 1, not being -1 and 1, then that geometric series will converge. But an infinite geometric series will diverge, means that its infinite summation will be infinity if the absolute value of r is greater than or equal to 1. So if r is less than or equal to -1, or r is greater than or equal to 1, this infinite geometric series will diverge. It will not come down to just one number. It will come down to infinity. And I'm willing to say that infinity is not necessarily a number, but a concept. So for the following series below, what I'm going to do is find the value for r, see if the absolute value of r is less than 1, or see if the absolute value of r is greater than or equal to 1. And from that, I'm going to determine whether the infinite geometric series converges or diverges. So I've got the work already done for us, but let's at least walk through it a little bit with this still being shown. I see that I have this series 3 plus 12 plus 48 plus 192. I can find r by doing 12 divided by 3, or 48 divided by 12, or 192 divided by 48. I see that r is equal to 4. I know that 4 is greater than 1. So my absolute value of r is greater than or equal to 1. So I'm willing to say that this infinite geometric series will diverge. Its summation will become infinity. Looking over here, I see that I have 2 minus 1 plus 1/2 minus 1/4 forever. I see that r is equal to -1/2. I can do -1 over 2, or I can do 1/2 over -1, or -1/4 over 1/2. So I see r is equal to -1/2. I know that the absolute value of r is 1/2 is less than 1. This series is going to converge. I don't know what that summation is going to be yet. That's next. But I just know that it's not going to be infinity. Similarly, if I was given something in summation notation, I just need to find r, and r is this number right here. I see that r is 2/5. I know that the absolute value of 2/5 is 2/5. That's less than 1. This summation, an infinite sum, is going to converge. It's going to be a number. I don't know what it is. Later I'll find it. And then another summation. Notice my value for r is 3 over 2. I know that 3 over 2, its absolute value is 3 over 2. I know that that's greater than 1. This summation will diverge. The summation is going to be infinity, or in the case of this -8 over 9 in front, it's going to be negative infinity. But we can determine whether an infinite series will converge, and if it does converge, then we want to know what that summation is. The sum of an infinite geometric series can be found by the following equation. S sub infinity, so the sum of the infinite amount of terms is going to be a sub 1 over 1 minus r. And again, notice that stipulation where the absolute value of r is less than 1. This is telling me that this series converges, and we need to have a converging series to find its sum. Notice we just need to know two things. The first term, a sub 1, is going to go in the numerator, and the common ratio r, it's going to be 1 minus r in the denominator. So I've got two examples for you. And again, we're going to evaluate each infinite geometric series described. One is described as a geometric series. Notice it's all the terms being summed together. I don't tell you how many terms because there's going to be an infinite amount of terms. And the other one is written in summation notation, where I know the first term is 2 and the common ratio is r. Over here, 27 over 2 plus 9 plus 6 plus 4. I see that the first term is 27 over 2. The common ratio, I could take it by 6 divided by 9, or 4 divided by 6, or 9 over 27 over 2. But I see that the common ratio is 2/3. I know that the absolute value of 2/3 is less than 1. I know that this series converges, therefore I can use this infinite sum formula. So I substitute a sub 1 in the numerator, 27 over 2. And then 1 minus r is 2/3 in the denominator. So 1 minus 2/3 is 1/3. Rather than dividing by a fraction, I want to multiply by its reciprocal. The reciprocal of 1 over 3 is 3 over 1. I get 81 over 2. So the sum of this is going to be 81 over 2. So this infinite sum converges on the number 81 over 2. Similarly, over here, I know that the first term is 1. I'm sorry, the first term is still 2. I'm going to put 2 in the numerator. In the denominator, I'm going to have 1 minus r. R is 3 over 5. I end up with 2 over 5. I know rather than dividing by a fraction, I'm going to multiply by its reciprocal. So 2 over 1 times 5 over 2 simplifies to 5. This infinite sum is just 5. But now I want to come back to our opening question. What is the sum of this infinite series below? And this is what we're starting off with. I could use the formula. And notice my first term is 1, and my common ratio is 1/2. So 1 over 1 minus 1/2 is 1 over 1/2. Rather than dividing by a fraction, I'm going to multiply by its reciprocal, and I get a sum of 2. But there's a beautiful graphical solution to the problem. And so notice I'm starting off with 1. And so here's 1, right? Let's use a square to represent a full unit. And the area of the square is going to represent partial. So notice I next have 1/2 that I'm going to add in here. So here's half of that square. So now I have, as a graphical representation, I have 1 plus 1/2, so the sum of the first two terms. And now I want to add a quarter. And then I want to add an eighth. And then I want to add a 16th. I'm taking half of what's left every time. And then I want to add a 32nd. And then I want to add 1 over 64. And then I want to add 1 over 128. And if I were to continue this forever, I hope you can see that I would fill in the entire area of this square of unit 1. So the infinite sum of this would be 1 plus 1, or 2, which is exactly what we got from the formula. I just love this graphical solution. I did assign some practice to find the sum of infinite geometric series. It's seen below. Good luck. Email me if you have any questions.